So the whole point of polynomial long division and synthetic division is to make use of the remainder and factor theorems. So we'll look first at the factor theorem, and it says, I'll be using lots of shorthand here, a polynomial, so that's a fatty P, that means polynomial, f of x has a factor x minus c if and only if, and the shorthand for that is IFF, if and only if the f of c equals 0. So that basically means if I divide a polynomial by some factor x minus c, then I need to get a 0 remainder in order for that factor to be a factor of the polynomial. So let's do an example to show. So we want to determine whether x minus 5 is a factor of x cubed minus 18x squared plus 60x plus 25. All right, so we're going to use synthetic division because we have a binomial of degree 1 with a leading coefficient of 1. So I'm going to first double check that I have all my x's, 3, 2, 1, 0, done. And now use just the coefficients, 1, negative 18, 60, and 25. And then I want to divide by, remember, it says here, and when we use synthetic division, we want to use the opposite sign, so 5. And in that case, check it out, we're looking to see if x minus 5 is a factor of the polynomial. If it is, then the f of positive 5 has to equal 0. So we're going to put in a positive 5. So now I bring down the 1. 5 times 1 is 5, and add minus 13. 5 times negative 13 is negative 50, 65, add 5 times negative 5 is negative 25, I add, and I get a 0. That means it is a factor. So the factors of this polynomial are, this is the remainder, this is the constant, x to the first power, and x squared. So at this point I can write the polynomial as x minus 5 times x squared minus 13x minus 5. Now, no two numbers multiply to give me negative 5 that add to give me a negative 13, so I know that this is a fully factored quadratic trinomial. And I've gone as far as I can with this. But let's look and see what happens. What if I had tried instead, for the very same problem, the factor x plus 5, which means I would divide by a negative 5. Same thing, 1, negative 18, 60, and 25. So I'm going to bring down the 1. Negative 5 times 1 is negative 5. Add 23. Negative 5 times negative 23 is going to be a positive, and 5 times 23, well, 5 times 2 is 115. So positive 115. And then negative 5 times 1, 7, are you kidding me? That'd be 500, right? Well, we know the answer is going to be negative. 500. 5 times 7 is 350. 5 times 5 is 25. 5, 7, 875. Plus 25 is negative 850. So we have a remainder of negative 150. You might think that this is kind of a big waste of time because we didn't find a factor, but it's not, because we also have the remainder theorem, and the remainder theorem says that if you have a polynomial, again the shorthand for polynomial, f of x, and if you divide it by x minus c, so we're dividing it by the factor, if you get a remainder r is the value of the f of c. So what does that mean? That means that if I plug negative 5 into the original function, it'll come out to be negative 850. So let's see if that's true. The f of negative 5 equals negative 5 cubed minus 18 times negative 5 squared plus 60 times negative 5 plus 25. Okay, so negative 5 cubed is negative 125. Minus 18 times 25. 5 times 8 is 40. 9, 16, 2, 3, 0, 9, and 6 is 15. Carry the 1, so 450. So this is going to be a negative 450, or positive, yep, negative 450 plus, nope, negative 60 times 5. 6 times 5 is 30 with another 0, so 300 plus 25 equals, let's add these all up. Well, negative 100 plus 20, negative 125 plus 25 is just negative 100 minus 450 minus 300. So now I have all negatives to work with. So 450, 550, 6, 7, 850, negative 850. And even though this was a little bit of work, it was way less work than doing all of this and having to do all of these calculations in here. So the remainder theorem is a quick, easy way, a quick way to check values that are function values at some input. And the factor theorem is a great way to find roots and factors, or factors, and to do factoring when you have higher order polynomials. So let's do one factoring problem using synthetic division. So let's factor f of x equals x cubed minus 2x squared minus 13x minus 10. So we want to factor this. Now, first thing is we want to use synthetic division, 3, 2, 1, 0, so I can set it up as a 1, negative 2, negative 13, negative 10. But now I want to come up with some good choices to divide by. And remember when we did this in Algebra 2, we had a way to determine good guesses. Any factor, not every factor, but any factor of this polynomial, or any solution of this polynomial, can be written in the form of plus or minus the ratio of a sub 0, or the leading coefficient, or the final coefficient, right? So a sub 0, which is here, and the leading coefficient. Okay, so it's a plus or minus some combination of the factors of the constant and the leading coefficient. So in this case, good guesses would be, well, the factors of 1 are just 1 and 1, right? So 1 for the leading coefficient. And the factors of 10 are 2 and 5. So that means in this case, good choices are going to be 2 over 1, plus or minus 2 over 1, and plus or minus 5 over 1. And plus or minus, don't forget there's a factor 1, and plus or minus 1 over 1. So that means I want to try 1, 2, and 5, positive and negative. So let's start with positive 1. So I put in a positive 1, do some quick synthetic division, bring down the 1, 1, negative 2, plus 1 is negative 1, negative 1, negative 14, negative 14, I get a remainder, so this is not a factor. So now let's try negative 1. So bring down the 1, negative 1, that's negative 3, positive 3, oh, this is looking good, which gives me a negative 10. Negative and a negative is a positive 10. My remainder is a 0. So I know that one of the factors of this term is x opposite sign plus 1. And what's the rest of it? I have, let's see, remainder is 0. That's to the 0, 1, 2 power. So I have an x squared minus 3x minus 10. So these are two of the factors, but I think I can go a little bit farther. So I have x plus 1 and x minus 5 and x plus 2. So this would be the fully factored form, and I use synthetic division to do it. Now, if I had a higher degree than 3, I would have to use synthetic division more than once. But as you saw, it's not a very cumbersome job to do. So let's go over what we've done. We got two theorems, both using the same form of division. You can use long division, obviously, but synthetic division is much nicer. If you run a number, which is the presumable solution to a problem, if you run that number through synthetic division and you get 0 as a remainder, then you know that the opposite of that number, or the factor that would produce that number, so, well, that's not where that goes, right? So x minus 5 equals 0, then you would get x equals 5. You know that the factor that would have given you that solution is a factor to that polynomial. I might have said that in way too many words, but hopefully you can figure that out. And if you put a number, a presumable solution, into the synthetic division and you get a remainder, it's not useless information. It's not a factor, but it is a solution. And remember when we were talking about graphing, sometimes you just have to plot points to kind of get a feel for the shape of the graph, and I recommended that you not do it, that you dot it in when you don't know where the turnarounds are. Well, if you've already done the synthetic division looking for the roots and you have a few points figured out, because this point on this graph for this function, the point -5, -850, is on the graph, it can be useful, and you might as well plot it on the graph and use it when you get there.